Hi everyone, in this snack I would like to talk about lutetium production and in particular the two different types of lutetium-177 products that you get from the reactor. And this is just a very nice picture of a reactor. I love the blue light coming out, it's very cool. It's a Cherenkov rays, just for those who are interested. So radioactivity indeed does glow. So here is just to start out with what sparked my interest in this particular topic. We treated a lutetium patient for neuroendocrine tumors, and you would see that here on the February scan there is a lot of accumulation in the liver where the tumors are. This corresponds with the PET-MIP image. Then in April, when we gave another lutetium dose, there was all of a sudden very little activity accumulated. And then the next dose that the patient got, there was again a lot of activity accumulated. It was the same on the posterior images, as you can see. So what was going on with this patient? Well, we realized due to COVID, we had to use another product. So these scans in February and June was with the lutetium non-carrier added product that was made in high specific activity, and the one in April was a lower specific activity product called the carrier added lutetium. So with our own eyes we saw that the quality of our patient's treatment was lower with our one product than the other, and I had to understand this. So first a few concepts to explain. Specific activity is the activity per quantity of a radionuclide, and it's a physical property of that radionuclide. So it's the amount of activity in radionuclidic form. Molar activity is, however, measured the amount of radioactivity per mole of the compound, which is your radiopharmaceutical. So when we talk about specific activity, we are talking about the radioactive element, and when we talk about molar activity, we are talking about your radiopharmaceutical and how radioactive each of these are. So you get low activity and high activity. There is a spectrum, and it also depends on how long your radionuclide or your radiochemical has been irradiated. So there's a lot of factors, and then you get the three common methods of describing radionuclides. The one is carrier-free, which means there is no other species in this mixture. It's only the lutetium-177, for instance. There is no other non-radioactive or other radioactive components in this. Non-carrier added is how it is in real life. So carrier-free is an ideal that we will never get to. Non-carrier added says that there is so little contamination that you can ignore it. So it's mostly lutetium-177 with a high amount of activity. And carrier added is when the product has other cold isotopes in that is similar to the product. So your lutetium-177 can be contaminated with lutetium-175. It is carrier added, there is other stuff in. So why do we have two different lutetiums available, 177? It is the two reactor methods of production. So for lutetium-177, you would buy the more affordable and available lutetium-175. You would irradiate it to become lutetium-176, and that lutetium-176 will become lutetium-177. There is also a metastable lutetium involved in some form. So here you have four types of lutetium that can be present in your compound, and as you know, isotopes are not generally well split from each other. You know, if there are true isotopes, all of them are lutetium, there is not a good chemical method to split one isotope from another. This is problematic, and the yield of this is very low because you have a lot of the cold lutetium in this mixture as well as lutetium-176. On the other hand, lutetium-177 non-carrier added is made by an indirect method. Ytterbium-176 is irradiated to make ytterbium-177, which decays to lutetium-177, And these are not isotopes from one another. They have two different chemical compositions, so you can split them off. You can purify lutetium-177 by more user-friendly methods. So you can get high specific lutetium-177 activity and without contamination of any other isotopes of lutetium. So here is a very complex table that you can pause and look at if you are interested in this more specific information, but it definitely says that there is a maximum activity yield for lutetium carrier added, whereas lutetium 177 non-carrier added definitely doesn't have a threshold. There is only one lutetium isotope in lutetium non-carrier added, where there is many in 177. High specific activity for non-carrier added, lower specific activity for carrier added. What do I mean by specific activity now again? Here is your direct method, where you have different lutetiums together with the orange lutetium that you really want. That is the one you want. So you can see it's kind of in a mixture where there is all the different other lutetiums and you cannot chemically separate them. The indirect method has a lot of lutetium radioactive, and then it has ytterbium-177 in between, but you can separate these two. So you can take them away. Now you have a very high specific activity lutetium by the indirect method, whereas your direct method is still not only lutetium-177. You label it with your vector, in this case prostate-specific membrane antigen therapy, to change it by distribution. When there is cold lutetium, the PSMA will bind to it exactly the same as lutetium-177 because they behave the same when they are isotopes of one another. The indirect method, no problem. Then you go to your tumor. This is where we eventually end up to treat, and you will see all the different lutetium PSMAs are binding. If they're radioactive or not, that doesn't make a difference. So there is 3 receptors filled with radioactive lutetium, and here all the receptors are filled with non-radioactive lutetium, pretty much like that picture we saw when we started out. There is too little lutetium at the tumor sites to even visualize it. Just to mention, you will see the amount of specific activity in gigabecquerel per milligram is way higher in the non-carrier added products currently available compared to the carrier added. So there is a big difference, and that also influences how long you can use this therapy and all the other implications of how strong the therapy. Now, there is a shortage of lutetium-177, although people are working on it, and there is a significant growth of demand for lutetium products. So there is only a few facilities in the world that can make lutetium non-carrier added. So we can still use the carrier added. We just have to be more specific of for which cancers do we use this. It depends on the availability of the target, the receptor. If it's a tumor with very little receptor expression, it's probably not a good idea to use carrier added. But if it is an area of interest that has a wide expression and there is no limitation on the amount of binding sites, you can still use carrier added. So radiosynovectomy, bone pain palliation, and hepatocellular carcinoma are all great ideas for the use of lutetium carrier added. In some instances, I would even say if it's widely spread prostate-specific membrane antigen targeting for prostate cancer, carrier added lutetium can still work. When not to use, here I said prostate, neuroendocrine tumors, those are the ones that you have to be more careful, especially neuroendocrine tumors because the receptors are not so widely expressed. So here is also an additional thing to take into account, that the carrier-added lutetium-177 has a radioactive byproduct called lutetium-177 metastable. It has a long half-life, and it will make your waste management quite substantially more difficult. Just to stop off again with this image. Now you understand that there was non-carrier added lutetium and they bound to all the receptors. Here, the carrier added had some cold lutetium mixed in and it wasn't binding to the receptors. All the radioactivity wasn't binding to the receptors because some of them were blocked off by cold radiopharmaceutical. This is something you do have to consider. If you've liked the video, please like it, and if you didn't, unlike it. Also give me some comments down below of where you think I made a mistake or you have a different opinion, and then also what you want to see next. And then I also want to thank BioRender for giving the scientific community such an amazing program for graphic illustrations. It really does help a lot. Thank you.